Starting with the lymphatic and immune systems chapter, which really should be separated into two chapters. There is a very close connection between the lymphatic system and the immune system, but there are some differences, and they really would benefit from being in two separate chapters. Because of how the schedule is worked out, we have today and then we have a week and a half off. It kind of works out that I'll be able to talk about the lymphatic system today, and then we'll start with the immune system next time. Now, as far as sort of the units in the course, in the old way I used to run the course and I had these major unit tests, there's one test over the autonomic and endocrine systems, which, as far as the book's concerned, are contained within the regulation, integration, control unit. And then there's a cardiovascular unit, which is here within fluids and transport, the first three chapters. Then I did the immune system as its own unit, because it's kind of a big thing on its own. And then environmental exchange, which is respiratory, digestive, and urinary systems, and then the reproductive system in with that, just because it had no other place to put it there. What I'm saying here is that the book's actually set up by putting the immune system in with the cardiovascular system. But I'm going to really treat it, and we're going to spend time in class on it as if it's sort of its own unit. So we're going to start with today with the lymphatic system, and then when we get back, we're going to be looking at the immune system, which will probably take more than a week to get to understand it fully. However, the book puts it in here, one, because there's not a good place to put it by itself, and two, because of the lymphatic system, it fits in with the cardiovascular system. It's an extension of circulation. And before I actually get into the lymphatic system stuff, I'm going to start by going back to the blood vessels chapter and the unit on capillary exchange. I ended with this material talking about blood vessels last time. So I want to pick up with this because it's really the bridge between these two things. So I was showing you as we move into the capillaries from the arterial side, blood pressure is 35 millimeters of mercury, which is opposed by an osmotic pressure that's about 25 millimeters of mercury, leaving a net pressure of 10 millimeters of mercury, which helps to force material out of the blood, filter things out of the blood. On the other side, blood pressure is dropped off as we move through the capillary bed, so that on this side, the blood pressure is now down to 18 millimeters of mercury, and the osmotic pressure is still the same, because that's not dependent on where we are in the circulatory system. So the net difference here, kind of redundant to say that, is 7 millimeters of mercury, representing the force that's moving things out of the tissue and back into the blood. Filtration and reabsorption, that's moving things out of the blood and back into the blood. Mainly what we're filtering out of the blood are nutrient type things like glucose or amino acids or oxygen. And what we're reabsorbing are waste products like urea, creatinine, carbon dioxide, those sorts of things. But those aren't the only things that are moving. All of that's taking place within a fluid environment, within water. And so filtration and reabsorption also means that there's movement of water out and back into the bloodstream. The difference in the pressures here means that that movement of water is not equal. More water leaves the system than comes back into the system. And so water accumulates in the extracellular fluid. I just want to talk a little bit about what those fluids are and to define them. So In the blood, we have plasma. Yes. That's within the bloodstream. So the double line I'm putting here represents the blood vessel wall. And then outside the bloodstream, we have what's called interstitial fluid, which is extracellular fluid of tissue. Okay. These are not the same thing. Okay. They're both extracellular fluids, but what's found dissolved in the plasma is different from what's found dissolved in the interstitial fluid. The biggest difference is plasma proteins. Plasma proteins do not filter out of the blood into the tissue. They stay, as do blood cells, but we're not talking about the cellular component. But all of the small molecules that are in plasma can move out into the interstitial fluid through that filtration. In the reabsorption, the components of interstitial fluid will move back into the plasma. And those are also not exactly the same. There are large proteins, for the most part, in interstitial fluid, which will not move back into the blood. The primary one is collagen. What happens if collagen gets into the blood? Why? Yes, that's correct. What do you activate in the blood? Platelets, right. Thrombocytes, I think is what you're trying to say. Yeah, so we definitely want to keep the collagen out, and it's not going to move back into the blood in that reabsorption phase. Okay. Now, let's see. Here at the end of this section in the blood vessel chapter, they mention lymphatic capillaries, but they don't actually address the lymphatic capillaries. So we need to move to the lymphatic system. Is that where I want? Yeah, this is it. So here we see a figure. Come on. And we'll talk about the other things in this figure in a second, but I want to concentrate on this circle right here. So obviously the red things here are representing the bloodstream. Okay. Red's just used there as a matter of convenience. What state the blood is in, oxygenated, deoxygenated, isn't terribly important. And we see red blood cells in the blood there. And then outside of the bloodstream, we see cells just representing cells of whatever tissue this is. It's just labeled tissue cell. And then running through the tissue, kind of interspersed with the blood capillaries, are these green vessels, which are called lymphatic capillaries. Blood capillaries, as we learned in the last chapter, are found between the arterial flow and the venous flow. Arterioles give rise to capillaries, and then venules come out from the capillary beds. Lymphatic capillaries are a little different. They're the end of the circulatory system. Now, by end, I actually mean beginning, which might sound kind of silly, but there's nothing beyond them. These arrows represent fluid moving into the lymphatic capillaries, and they'll move on along through the lymphatic system. We see here in the picture two cusps representing a valve, and there are valves in lymphatic vessels. At this point, the vessel is supposed to be larger, so we don't call it a capillary anymore. Capillaries don't have valves in them, but the larger lymphatic vessels do. So the fluid is absorbed into the lymphatic capillaries. It moves on into lymphatic vessels, and it drains that fluid out of the tissue. That fluid's accumulated within the tissue because it's come out of the blood capillaries and it's not being reabsorbed because of that difference in the pressure behind filtration and the pressure behind reabsorption. Less water gets back into the blood in reabsorption than the water that comes out of the blood at filtration. And to make up for that disparity, that extra fluid is absorbed into the lymphatic capillaries and moves on through the lymphatic vessels. Now, the lymphatic vessels are carrying essentially that interstitial fluid along. It's just we call it instead lymph or lymphatic fluid. It is, by composition, the exact same thing as interstitial fluid. The difference is just where we find it. When it's in the extracellular space of the tissue, it's interstitial fluid. When it's in the lymphatic system, it's lymph or lymphatic fluid. So again, plasma is different from interstitial fluid because of what does not move from the plasma into the tissue or from the tissue back into the plasma. Lymph, however, is essentially the same thing. One of the things I use to sort of define interstitial fluid is that it contains molecules that don't get into the plasma, like collagen. We wouldn't really find collagen in the lymphatic fluid very much, mostly because collagen fibers are anchored to something in the extracellular fluid. But there can be some loose collagen that might get out of the tissue, and it can move through the lymph. But really, it should be anchored somewhere. It should be attached to a lymphocyte or something. I'm not a lymphocyte. It should be attached to a fibroblast or something like that. So it's not too common to find collagen per se in the lymphatic fluid, but it is still going to be part of the lymphatic system, which we'll look at a little bit. So now, that was to explain the different types of fluids and their relationships to each other. I also want to talk about the functions of the lymphatic system. And there are essentially three. The main thing it does, which is what I just explained, is to recover fluid from the cardiovascular circulation. So that fluid that ends up in the tissues as interstitial fluid, because more water comes out of the blood than goes back in, will then move into the lymphatic system and eventually be returned back to cardiovascular circulation. So that if it wasn't reclaimed, if it wasn't recovered, eventually all of the water would move out of the blood. So we need to get that fluid back into cardiovascular circulation. Now, that's really the main point of the lymphatic system. But from that, the lymphatic system is capable of doing two other things, which are really extensions of that fluid recovery, recirculation, whatever you want to call it. First off, it transports dietary lipids. Now, what's special about lipids versus other macromolecules? What sets it apart? Yes, and what do we call that? When something doesn't mix with water, we call it what? Hydrophobic. Right. Lipids are hydrophobic. The other macromolecules are hydrophilic. And when I say dietary, I'm really talking about nutrient molecules, which would be lipids, proteins, and carbohydrates for the most part. And so of those macromolecules that we absorb from our diet, lipids are hydrophobic, okay? And so we don't really want them going into our bloodstream because hydrophobic molecules will tend to clump together and form droplets, like oil droplets or something like that. And if we have that, it can act kind of like a clot and gum up the works in circulation and result in a stroke or something causing a heart attack or something like that. Okay. So dietary lipids actually leave the digestive system through the lymphatic system before they get back into the circulation to be distributed to tissues. We'll talk about that more in terms of the digestive system when we get there, but understand that that is a function of this. And it's really just that the lymphatic capillaries in the digestive system are recovering fluid from circulation. And with that, they're also picking up the hydrophobic lipids preferentially. Okay. The other thing that it's capable of doing is, am I going to spell that right? I don't think I was just spell checking this. I reserve the right to spell that wrong, that word wrong. But immune surveillance, okay? What this means is the immune system basically uses the lymphatic structures to pay attention to what might be in your body and what might be pathogenic. And that's really why the lymphatic system and the immune system are together in a chapter, because often we just think of the lymphatic system as being the anatomy behind the immune system. That's not exactly true. It's more because of what the lymphatic system does in recovering this fluid that it's able to also play a part in the immune system. It goes a little bit further than that. We'll talk about more detail, but that's basically the idea. And again, it goes back to this recovering fluid thing. As the interstitial fluid is moving into the lymphatic system and draining that away, anything that's dissolved in that tissue is going to come along too. So if there are virus particles or bacteria or any type of cell really can get into the lymphatic system to some degree. Size is a little bit of a barrier, but it is possible for certain things to move into the lymphatic system other ways besides lymphatic capillaries. And we'll see a lot of white blood cells in the lymphatic system because what they're doing there is really sort of paying attention to what's present and surveilling potential immune threats. But it's really just building off of, again, that recovery of fluid. Oops, we're done with that one. So what we want to think about is what makes up the lymphatic system. And this picture kind of gives us a broad overview of the things that are involved. So I pointed out the lymphatic capillaries, which are found throughout the tissue. Really, this picture here, why it's suggesting to be an inset here, I'm not quite sure. It's not a very accurate representation there. But no, I think I kind of understand what they're doing. But what's in this circle here really represents what we'd find in any tissue anywhere in our body. Okay, there's blood vessels throughout all of our tissue, capillaries, and that sort of thing. And so there's always going to be lymphatic capillaries there also. Anywhere that you see an artery and a vein, artery taking blood to an organ and vein carrying blood away from an organ, or vice versa for the heart, you're going to see lymphatic capillaries. Okay? You're going to see lymphatic vessels. For instance, in A&P1, you learned about the structure of bone. In the central canal of an osteon, there's blood vessels, arteries and veins. There's also going to be a lymphatic vessel going through there because you're really going to see all three of those together, not just arteries and veins. There's usually going to be lymphatic vessels in the neighborhood because they're going to help drain that excess fluid away. In the picture here, they've drawn all of these green lines representing lymphatic circulation. It's much more extensive than this picture suggests. If they were to draw all of the lymphatic vessels in, then we just see this completely green woman because they're everywhere. Okay? This is just highlighting some of the ideas of where they are. Again, the lymphatic capillaries are the end of the system, really where the fluid moves into it to be moved back. So we're going to see it out in the extremities, so in the hands and feet, which are not in this picture, and then we're going to have vessels carrying everything back. Eventually, those vessels connect back up to the cardiovascular circulation at the subclavian veins, which are some of the veins represented there. Okay. This picture is also showing us several organs that are part of the lymphatic system. The main type of organ is a lymph node. Lymph nodes are found scattered throughout the lymphatic circulation. So the inset that they show here is supposed to say there's a lymph node that would be located right there. We can see some little enlargements here and there along all of the different circulation. Those represent lymph nodes. And they're much more prevalent than this picture suggests again. We do tend to see lymph nodes located around major joints. They don't exactly point them all out here, but there's going to be cervical lymph nodes around your neck because you move your neck quite a bit. That's a big joint. There's going to be axillary ones at the armpit. There's probably going to be some around the elbow. I don't know what those would be called. There's quite a bit around the hip joint called inguinal.
Cuboidal.
Oh, thank you. Cuboidal. Inguinal ones around the hip. There's going to be some at the knee, et cetera, et cetera. There's no pump like the heart for the lymphatic system. So instead, the lymphatic system has to rely on passive means of pumping. And basically, by having all these lymph nodes at the joints, whenever you move your joints, you're going to squeeze the lymph nodes. And that squeezing lymph nodes helps to move the fluid through the system. And we'll look at the structure of the lymph node in a little bit more detail in a bit. The other ones that are pointed out here, the tonsils, they have an adenoid up here, which is kind of like a variation on a tonsil, but in a weird location. Tonsils, the thymus, which is a gland located just anterior and superior to the heart, the spleen, bone marrow represented by the femur here, and then there's a lot of lymphatic tissue in mucosa-lined organs, and they're representing that here with the intestines. Okay. Somewhat unfortunate in this picture, they've colored it blue as if it's a vein, but this big enlargement here and then the vessel going up from it, these should be colored green because they're part of the lymphatic system. This structure here is called the cisterna chyli. Oh, that reminds me, I forgot to put something in here. Now, cistern basically just means a large storage place. In ancient times, cisterns were basically holes in the ground that you put things to keep it at a reasonable temperature. I kind of think of, in the desert or something like that, people would bury urns of things, and now archaeologists are finding these things and uncovering them. But the idea is by putting it underneath the ground, the temperature is much more stable down there and things can last for longer. Nowadays, that's what we call a cellar. Okay, so you put food or whatever down in the cellar and it should last a little bit longer because the temperature's more stable. If you have a cellar or a basement now, right now, you go downstairs, it's probably a little colder than the rest of your house. And then in the summer, you go down there because it's a little bit colder than the rest of your house, which is a good thing in summer. But the temperature down below the ground level is pretty constant. It's about 55 degrees Fahrenheit. I can't remember how deep you have to go for that to be constant, but that's what a cistern is, just a place where things are stored. chyli is referring to another type of fluid, which I really should add up here. Chyle is lymphatic fluid plus lipids. Okay. So I told you earlier that one of the functions of the lymphatic system is to transport dietary lipids. And so the lymphatic fluid that has a lot of lipids in it is really referred to as chyle. And so cisterna chyli is just talking about a place where we find a lot of lipid-rich lymphatic fluid. And back to this picture. Again, it should be colored green, but it's blue in this picture. That's the cisterna chyli. Okay. Now, why do you think it's located right there? That position is actually relevant to what that's for. Sorry, the mouse is off of it now, but it's this thing right here in the middle. Why would we put something called the cisterna chyli right there? What's it right next to in the picture? The intestines. What do the intestines do? It's where we absorb dietary molecules. So all of the lipids that are being absorbed in the small intestines, and then all the lymphatic vessels from there carrying those lipids are going to go to the cisterna chyli. That's why it's called that. The vessel extending through the thorax, going sort of straight up from that picture, that part of the picture, that's the lymphatic duct. Sorry, the thoracic duct of the lymphatic system. And so that's carrying that lymph fluid up. Now, what's not obvious in this picture because of how they've represented the small intestine, that sort of thing, there's more going into the cisterna chyli than just the vessels coming off the intestines. There's also all of the vessels coming from the lower body. Okay. So all of the lymph from the legs and the abdomen drain into the cisterna chyli, and then the thoracic duct, which is what's represented here, goes up and attaches to the subclavian vein here. Now there should be another picture of this. Yeah. So all of the stuff that's represented in yellow in this picture are regions of the body that drain into the cisterna chyli. Okay. So everything from the cisterna chyli down, left and right. And then from the cisterna chyli up, that doesn't drain in the cisterna chyli, but that feeds into the same system. And so the rest of the left half of the body drains here. And so this big vessel that we see coming up here, that's the thoracic duct, what's coming off the cisterna chyli. And a few smaller vessels join up with it. And they all drain into the left subclavian vein. The purple in this picture representing the right side of the body from the cisterna chyli up. All of that stuff drains on the right side. We don't see a huge vessel like on the left side, just all the little vessels like on the left side that are draining from the head, neck, shoulders, and thorax. That all goes into the right subclavian vein. Between those two, we're getting all of the fluid back from the body. There just happens to be a little bit of asymmetry here because from the cisterna chyli down, both sides of the body drain in there, really because the intestines can't be separated into the right and left side. So all of the intestines drain in there, and then all of the lower body drains in there also. And then that all goes to the left side over here. The right side is just everything from that point up, drains into the right side. But we have that sort of separation of what's draining in the two systems. And again, this is the cisterna chyli. It's colored blue for whatever reason, but it's part of the lymphatic system. So I want to talk about some of those. I'm not going to get into this a whole lot of detail right now, but I do want to mention it because the book points it out here. This is actually a picture that's in the blood chapter about how the different types of blood cells are made from the red bone marrow, which I talked about when we were dealing with blood. What's important here is that stem cell, the hemocytoblast, can become a lymphoid stem cell. Okay? And lymphoid stem cells give rise to lymphoblasts, which then give rise to lymphocytes. Lymphocytes, you might notice, have the same root as the word lymphatic. Okay? We see lymphocytes throughout the lymphatic system. And they're largely concerned with a lot of the functions there. The other side of this, the myeloid stem cell making all these other red blood cells, all these other blood cells, including the red blood cell and platelets, and the 4 other types of white blood cells. Some of them are concerned with immune function. Some of those white blood cells are. But the lymphocytes are kind of special, so they're sort of off on the side. And we're going to talk about those lymphocytes. There are 2 major types, B cells and T cells, which will be the focus of understanding lymphocytes when we get to that part of the section. And there are a couple of others that I'll mention. The plasma cells and natural killer cells are part of that too. But I want to talk about the lymphatic organs a little bit. Or I should say lymphatic organs and tissues a little bit more in depth. So we separate the lymphatic organs and tissues into 2 groups. There's the primary lymphoid or lymphatic organs and secondary. The primary ones are bone marrow, which isn't really an organ, it's just a tissue that's within a bone. And by that we really mean red bone marrow. The picture here is of should be the head of the femur. Yeah, head of the femur. So we're looking inside where the spongy bone tissue is inside the head of the femur, and within all of the spaces of the spongy bone tissue is red bone marrow. It's red because that's where red blood cells are being made. But that's just why it has that color. It's also where white blood cells and platelets are being made as well. And the white blood cells are the ones that we're most concerned with here. The other tissue, primary tissue or primary lymphatic organ, is the thymus, which I said a little bit earlier is located just anterior to and a little bit superior to the heart. We don't tend to see it in anatomical models because it gets in the way of seeing the heart. And by the time somebody is an adult, the thymus isn't really doing too much. So we kind of ignore it for general anatomy, but that's the case. Now, they don't have red in red bone marrow up here, actually for a reason. What are the 2 major types of lymphocytes that I mentioned a second ago? How do we refer to those?
B cells.
Yeah, B cells and T cells. And so what they're trying to do with the book here is to associate in your mind B cells with bone marrow and T cells with thymus. Now, the T in T cell, in fact, does stand for thymus. The B in B cell does not actually stand for bone marrow. It stands for the name of an organ that humans don't have. They're originally described in an animal model. I can't remember, some sort of bird, probably chicken. And birds have this organ that mammals don't have. So what the B actually stands for doesn't apply to us. But for our purposes, we can associate with bone marrow. And really, we mean red bone marrow. Yellow bone marrow is just adipose tissue, so it doesn't do anything. But you can keep in mind which are the primary lymphatic organs or tissues because they correspond to the B cell and the T cell, the bone marrow and the thymus. And then basically everything else falls into the secondary lymphatic organs or lymphoid organs. And the sort of go-to example of that is the lymph node. So let me pull up that picture here. The lymph node is sort of the characteristic lymphatic organ, both in structure and basic function. It's surrounded by an outer capsule, just an enclosing epithelial connective tissue membrane. But then what's inside of it is all reticular connective tissue, which is really the main tissue that we see in the lymphatic system. Reticular connective tissue under the microscope has various different appearances. There can be regions where there's a density of cells, and there can be regions where there's not a whole lot of cells present, right? So sort of a cell-free region. As we're looking at the tissue under the microscope, like in this micrograph here, the darker staining parts are going to be where there's a lot of cells, and the lighter staining parts are where there won't be a lot of cells. One thing that's characteristic of kind of all lymphatic tissues or lymphoid tissues, we see little clusters of cells within a nodule of the tissue with sort of a specialized cluster of cells within that. And those specialized clusters of cells here in lymph nodes we call germinal centers. But you'll see that kind of appearance in the tissue, sort of in all the different organs that we have to look at. And I'll point that out to you as we look at the other micrographs. Now, the thing about lymph nodes is they have lymphatic vessels attaching to them that fall into two groups, what we call afferent vessels and efferent vessels. Now, I make a big point of pronouncing those two words so you can tell the difference between afferent and efferent. Afferent means going towards, and efferent means going away from. Unfortunately, it doesn't really work well that the A in away does not correspond with the A in afferent, like we saw with arteries in away. These two words are really very general terms. We use them in a lot of different contexts in anatomy. So a lymphatic vessel going towards a lymph node is an afferent vessel. A lymphatic vessel going away from a lymph node is an efferent vessel, which we see where's the picture? In the picture here. There are in this picture 5 afferent vessels really in the drawing. They only label 3 of them, but the 2 off to either side would also be afferent vessels. And then there are 2 efferent vessels. There's always more afferent vessels than efferent vessels connected to lymph nodes. That way, we can increase the pressure in the system, again, passively. If you take 5 hoses and attach them to a water balloon for some reason is my go-to example of fluid movement. So 5 hoses going into the balloon and you only have the one opening on the balloon for stuff to come out, then what's coming out of that balloon is going to be under a lot more pressure than the water going into the balloon. Okay. I really need to get away from my water balloon analogies, but if these 5 vessels are all bringing fluid in and these 2 are the only way that the fluid can get out, then the pressure out is going to be increased versus the pressure in. So that, along with the fact that a lot of lymph nodes are at joints where they're going to be squeezed when your body moves, really helps to keep the lymphatic fluid flowing through the system. If we consider where there's areas without a lot of cells and areas with a lot of cells, we can see that there's sort of this pathway through the lymph node that fluid can flow. So fluid comes in through an afferent vessel, and it'll flow through most easily where there's fewer cells. It'll go from just beneath the capsule, which is the subcapsular sinus, down into these things called trabeculae, where there's still a lot of space. And then they'll eventually flow towards the middle of the lymph node and out through the efferent vessels. When you're fighting off an infection, one of the things that we're going to learn about in the immune response is the inflammatory response, which is going to have fluid accumulation associated with it. That fluid will accumulate in whatever tissue has an infection, and that fluid will move through the lymphatic system. And so as more fluid comes in here, that pathway through of least resistance through the cell sparse areas will kind of be overcome, and fluid will just flow through most everything as the lymph nodes swell with fluid too. If you ever tried to get out of going to school and telling your mom that your throat was sore, what was the first thing she did? She went to feel for so-called swollen glands at the base of your jaw, top of your neck. There are a lot of lymph nodes there, again, because it's at a joint. And if you have something causing an infection in your throat, those lymph nodes are preferentially going to be swollen. Okay? So if you're just saying, oh, I have a scratchy throat, and you're putting on your best scratchy throat voice to get out of going to school, you'll be caught in a lie very quickly, because if your lymph nodes aren't inflamed, if they're not swollen, then you're obviously not fighting off an infection. So this isn't just a trick that mothers can use to catch kids who don't want to go to school, but rather it's we're always going to see that. Swelling at a site of infection is going to translate directly into swelling in the lymph nodes as that fluid is moving. And as that fluid's moving, whatever pathogens present in the infected tissue is going to move through the lymph nodes also, giving the immune system a chance to do its job. Let me close those out. The spleen is kind of one big lymph node. The big difference is that it doesn't really have afferent vessels going into it. Instead, it's just getting a blood supply. So there's a splenic artery and the splenic vein, and that brings blood in. What's different, though, is the capillaries in the spleen, if we can even say that they exist, are sinusoidal or very, very porous capillaries. And all of the contents of the blood will really just spill out into the spleen. Now, the tissue separated out in the spleen into two major regions called the red pulp and the white pulp. The red pulp is red pulp because that's where red blood cells are accumulating as the blood's moving through. The white pulp, which is essentially the same thing as a germinal zone in the lymph nodes I just showed you, has a high concentration of white blood cells. So that's where it gets its name, white pulp. The spleen is really about filtering the blood. So any pathogens, any bloodborne pathogens will go through the spleen, even though they might not get into the lymphatic system through normal means. Also, old red blood cells will pass through the spleen, and white blood cells can get rid of those so that they don't live past their 120-day lifespan. So the spleen is really just a big lymph node for blood rather than lymphatic fluid. Looking at it tissue-wise, it does have sort of the same appearance with what we could call germinal zones within other cell-dense areas. But really, the germinal zones are what we call the white pulp, which is where there's a high density of white blood cells. And then outside of that, the blood's going to be accumulating, making that tissue look very red, and it's called the red pulp. Beyond that, we have what are referred to as lymphoid nodules or lymphatic nodules. The book puts tonsils in with that, which I don't entirely agree with. Tonsils are really a separate structure. But a case could be made for them being really overgrown lymphoid nodules. Tonsils are found basically around the oral and nasal cavities. They're primarily responsible for immune surveillance of airborne or foodborne pathogens. They're kind of like lymph nodes. They're the same kind of tissue. It's just they're different that they don't have, again, afferent vessels going into them. The fluid that's absorbed in in tonsils, instead of how they are in lymph nodes, is really the fluid from your nasal mucus and saliva from your oral cavity. And so pathogens that you inhale get caught in that nasal mucus, or pathogens that you ingest are going to be dissolved in that saliva. And so they'll move across the tonsils, whether it's the pharyngeal tonsil in the nasopharynx, or the lingual tonsils at the back of the tongue, or the palatine tonsils in the roof of the soft palate. Those are all positioned so that these fluids will move across them. In the micrograph down here, which isn't getting as big as I was hoping, you can see that there's germinal center kind of structure in the tissue, just like in lymph nodes. They point out something here, this crack in the tonsil is important. This is what's called a crypt. It's a crevice, whatever you want to call it, where that fluid that's passing over the tonsil can kind of get in. And if that fluid contains some sort of airborne or foodborne pathogen, that pathogen is going to get down into that crack also, into the crypt. If you were a pathogen, if you were bacteria that was just ingested, the bacteria is just looking for a warm, dark, moist place to reproduce. And crypts are perfect for that. So the foodborne pathogen can get down to the crypt and they can start to reproduce and form a little colony of bacteria there. The thing is on the other side of the membrane of the crypt, there's going to be a bunch of white blood cells. So it's sort of like luring the foodborne pathogens in, or airborne pathogens in, allowing them to set up house, raise kids, great schools in that neighborhood, all that sort of thing. But the neighbors are not very nice, okay? And so those neighbors are going to fight off that infection and be able to tell the rest of the immune system that whatever that was got into the body and is probably going to show up in the intestines or in the respiratory tract at some point. So the crypt is kind of a place to trap some of those things so the immune system can deal with it right off the bat and prepare the rest of the immune system to be ready for it later on. Yeah.
So is the palatine tonsils the tonsils that are removed if, like, you know, when kids get their tonsils removed?
Right, probably. Those are the two that we see that are swollen here.
So does that affect the way that we can fight off the airborne food?
So yeah, it does suggest that there be a compromise of that function to some degree, but part of the reason why the book lumps this in with the lymphoid nodules is because there's a lot of other tissue that does the same sort of thing down the digestive and respiratory tract, so it can kind of pick up the slack there. Okay. There are some things that if you have them removed, you need to pay attention to the loss of immune function. Like a splenectomy is usually accompanied with instructions to get regular vaccines and flu shots, and which is a vaccine, and antibiotic treatments whenever anything comes along, because the spleen being gone is a rather significant loss to the immune system. But after a tonsillectomy, there's probably not a lot of instruction to people to deal with that sort of thing. I would imagine if somebody has had a tonsillectomy and they tend to have throat infections more often, then their doctor will know that something needs to be done. But probably generally across everybody that has a tonsillectomy, to say, you know, you need to treat it this way or whatever, probably isn't as big of a deal. And that's because there are these other lymphoid nodules, which is referred to as a mucosa-associated lymphoid tissue, or MALT. Really, to some degree, you could say that the tonsils are kind of a super version of these. So just within the mucosal lining here, this is supposed to be the small intestine, there are little nodules of tissue. They look like just one part of a lymph node built into the area. They have germinal centers and that sort of thing. And they help with dealing with foodborne pathogens that have gotten that far through the system. Okay. Now, foodborne pathogens do have to pass through the stomach, and we get rid of a lot of stuff that way. Just the acidity and the digestive enzymes in the stomach will get rid of a lot of things. But if something does make it past that, then we have more lymphoid tissue here. Now, they're labeled Peyer's patches here, which is kind of an old-fashioned name, but the mucosa-associated lymphatic tissue is a little bit more modern and general term for them. Anywhere that we have a mucosal lining, we're going to see this. This happens to be the small intestine, but we'd see it in the respiratory tract, we'd see it in the digestive tract, anywhere else in the digestive tract. We'd see it in the urinary tract and in the reproductive tract. All of those have mucosa, so they're all going to have mucosa-associated lymphatic tissues. Now, they don't have a picture here, but I do want to take a second to talk about the appendix, because too often people have this very incorrect view that the appendix is a vestigial organ. You might have learned that back in, looking for a micrograph of this. You might have learned that back in grade school. Grade school students have probably heard of people that have had appendices removed or something like that. And so they'd say, well, obviously you can have it removed, so it's not a big deal. And grade school teachers tell this myth that the appendix is a vestigial organ. Now, this is a micrograph of an appendix. It has mucosa-associated lymphatic tissue with it also, just like the small intestine I was just showing you. But really, its only function has to do with what its lymphatic tissue is there for. The reason it usually gets called the vestigial organ, and the basis of this being a myth, is that it's different from the same structure in other types of organisms. In a dog, for instance, they have this part of their large intestine, which is our appendix. I don't remember what it's called in the dog. It might be called I don't remember what it's called. And it's basically where vegetable matter is fermented. Okay. Dietary fiber, cellulose from plants and that sort of thing, that we ingest, we can't digest. So in our large intestine, we have bacteria that break that down for us. And that's true in dogs, for instance, also. It's just for dogs, they do it in this little pocket, and that's where fermentation takes place. Now, if you have a dog and you've ever seen it eating grass, it's probably doing that because it needs to get more vegetable matter into that part of its digestive system. I'm not a veterinarian. I have no idea if that's at all true, but that's usually what I think of. For primates, our large intestine is very different from other mammals' large intestines. So this includes apes and other primates. Maybe not all primates, but we have adapted to a more vegetable-based diet. Not a vegetarian diet, but we do eat a lot more vegetable-based matter. And so our large intestine doesn't really need that same structure that a dog does, which is mostly carnivorous, because food moves much slowly through our much longer large intestine. And so all of that breakdown of dietary fiber happens in the rest of the large intestine, which would suggest for that function, yes, the appendix is vestigial, but the appendix is still necessary because it has a very important immune function to play, which is very similar to the tonsils. If grade school kids are willing to accept that the appendix can be removed and therefore is not necessary, why don't they have the same feeling about tonsils? And they very well might. But grade school teachers don't say that tonsils are vestigial organs. The appendix is basically the same thing as a tonsil, but in a different location. Those bacteria that help break down dietary fiber live in our large intestine. We don't want them moving from the large intestine into the small intestine. So the appendix is right there at that junction, and it plays a role in maintaining the proper distribution and population of bacteria in our large intestine. Exactly how it does that has been a matter of a lot of debate, but it does seem to play a role in that. Just like with tonsillectomies, of appendectomies probably do cause some loss in immune function, but probably not enough, and there's plenty of mucosa-associated lymphatic tissue in the neighborhood to play a similar role. But I would bet somebody who hasn't had an appendectomy is more likely to have intestinal problems crop up. And they'll just get used to, there's certain things that they don't want to eat too much of because it's going to cause problems. Okay. But as far as a specific medical advice of what to do, we don't tend to mention that for appendectomies like we do for splenectomies. Anyway, so that runs through the lymphatic system. Next time when we come back, which will be on the 24th again, we're going to pick up with this chapter and moving on from the lymphatic structures more into the immune function that the rest of the chapter is about. So have a nice long